Human behavior is inherently multimodal, and individuals use eye gaze, hand gestures, facial expressions, body posture, and to convey engagement and regulate social interactions. We have developed novel computational methods for measuring and analyzing the behavior of children and adults during social interactions and object-to-object interactions. With this method we can automatically collect fine-grained behavioral data. This project will enable large-scale objective screening for computational psychology and more effective delivery and assessment of therapy and behavioral surveillance. Additionally, many disciplines, such as education, advertising, security surveillance, emergency responses and customer relations, could benefit from this quantitative, data-driven approach of behavioral analysis. This will show you how the surveillance video files, which is sequences of image files, is processed to extract the behavioral features. The first step lies in the process is the reading of each frame into a width by height by 3 array. The red frames are categorized into pair of consequent frames where these pairs are processed using Sobel's edge detection method to extract the contours of the objects in the scene. Followed by this step, the alignment of the two paired images are matched and checked using the image correlation method to record the deviation of the object's geometry and position from one frame to another. Thus, the unqueried pixels gives the pivotal joints of the object and consequently facilitate us in determining the degree of freedom of subparts in each joints. The method is much computationally faster and precise than the currently used silhouettes extraction method. As depicted in the figures below, the subparts of the object based on the pivotal joints is divided into its hierarchical geometric structure. The advantage of this method is that we don't need to create new points in varying scenario of poses, as it is clustered into hierarchical geometric points which embodies the shape of object and already mapped into 3D coordinate space. Hence the missing information can be averaged of its children such that the several layers of clustered points marked with different colors can be pulled up to render the structure in cases of pose estimation. Now, the derived action sequence from the previous steps is encoded logically into code blocks based on the actions link with the previous sequence by forming bases for 3 parameters, that is, what, marked in blue, which represents child nodes, and where, marked in green, represents geometric space, whereas the successfully encoded action sequence represented by color red. Note that the encoding process is done as per the Zipf distribution to avail the advantage of sequence allocation by just calculating its class rank and frequency of appearance. A Buehrle network consists of a discrete set of Boolean variables, each of which has a Boolean function, possibly different for each variable, assigned to it, which takes inputs from a subset of those variables and output that determines the state of the variable it is assigned to. This set of functions in effect determines a topology, connectivity, on the set of variables, which then become nodes in a network. Here we have developed our own mathematically modeled synchronously evolving Boolean network, which synchronously evolves the relationship between input and output action sequence to anticipate the correct sequences in less number of steps, followed by fetching of data to recurrent fuzzy neural network to predict the action pattern. The advantage of using SEGM is that we do not need to provide the training dataset. It autonomously determines the relationship between each action sequence and trains the recurrent fuzzy neural network unsupervisedly. Hence, with the Zipf distribution along with SEGM can model the trend of action sequences without any human intervention. Finally, the sample output from the eye is shown below, where the color-coded sequence represents the position, child subparts of the object in the interwoven encoded sequence of it in blue, green and red color respectively. Also, the sample below shows the example where our system identifies the shoplifter marked in red thick bounding box and the theft or suspicious action sequence represented in thin red bounding box. Following are a few multidisciplinary scenarios of the eye as in action. The video below shows the sample results of market surveillance, where the customer's interest in products at the shop is analyzed via artificial intelligence. In this scenario, the system can be used, and like big data, this tool will help in reality mining to avail real-time targeted marketing, advertising, to come up with behavior influence market model, elderly care, crime reporting, emergency situation analysis, etc.